Alright guys, today we're going to talk a little bit about reactions of alkenes. In our last video we talked about reactions of alkanes. And so this time we're going to talk about alkenes. Remember that alkenes and alkynes, we're talking about unsaturated hydrocarbons, meaning those that have double bonds somewhere in them. So of course we're going to start out, and as before, we're going to try to keep things as easy as possible. We're pretty much going to talk about addition reactions in today's video. And an addition reaction for an alkene essentially works in a pretty simple pattern. You've got a double bond. Okay, and you're going to add something to it, and the thing that you're adding to it comes in two parts, and those parts are going to break apart, and they're each going to join one of the carbons that had the double bond. Okay, so those things are going to break apart, A and B break away from each other, and they form onto what was formerly the carbons where the double bond was in the alkene. Okay, so pretty straightforward. So let's talk just briefly about what's going on here. Anytime that we have a double bond, remember that we have a sigma bond and we have a pi bond between those carbons. That's where we get the double. So single bonds are always sigmas, and then when we get the double bond in there, it becomes a pi bond. So we're going to break the pi bond here. And what I didn't necessarily put in the video here, but you can see, is that we're also going to break the sigma bond that is of the other reagent. Okay, so there's a single bond here. We're going to break that sigma bond. So we're going to break those two bonds, just the pi. Now remember, the sigma is still here between the carbons. And so what we're then going to form is two new sigma bonds. Okay, so we broke a pi bond, and we essentially broke the sigma here, but we're now going to form two new sigma bonds. And this is important because these two sigmas that we form are stronger than the pi bond. And again, just remember that what's going on here is that we've got, whoops, sorry for the scrolling there, guys. What we have here is we've got a case where we've got carbon, carbon, and there was a double bond, but now there's just a sigma, and then there are two new sigma bonds attaching A and B. And so this is a more stable scenario, therefore that's going to make this type of reaction a little bit more favorable. Okay? So, of our types of addition reactions, I'm going to run through the different types real quick, and then we're going to talk about what's a lot more important to us, which is, of course, how does this happen? How do we know how this happens? What's the mechanism behind this? So the first type of addition reaction is a halogenation. We're going to add halogens on. So we've got 2-butene here. We're going to add chlorine to it, and that is essentially going to add 2 chlorines to it. Now you'll notice the first thing that should notice immediately different from this in alkanes is that both of the chlorines added. I didn't kick off a hydrogen and get HCl as a product, and that's because there is no extra hydrogen. I didn't actually lose any of the hydrogens here. I just added my chlorines. This is not a substitution reaction that it was in alkanes. This is an addition reaction. So one of the big differences is no lighter heat is needed in this case. And then we can also do this with other halogens, typically bromine. And in fact, bromine is a really good test. If we add bromine to compounds that we're not sure if they're saturated or not, they will react and they will turn color so that will tell us, hey, this actually is an alkene or an alkyne. It's not an alkane. So it tells us that something is unsaturated. Our next type of addition reaction is hydration. Hydration, what occurs is you're going to add your alkene to a water molecule. It has to be in the presence of an acid. And what that is going to do, we'll see why that acid is there. That's part of the mechanism. And what that's going to do is one of the hydrogens is going to attach on one of the carbons. The OH is going to attach on the other. So it really helps a lot in reactions generally. If you think about water, instead of just being H2O, if you think about it as being an H and an OH, those two things are going to attach on there. Okay, so that's a hydration reaction. And then we can add acids to it. So we can add a hydrochloric acid. What that's going to do is essentially going to do the same thing as a monochlorination for an alkane. So I'm going to get one chlorine added, and then this is obviously going to be a saturated carbon over here. Okay. The only acids that this tends to work really well for are the halide acids, so like hydrochloric, hydrobromic, and then sulfuric acid also we can add in there. And remember, sulfuric acid, just in case you've sort of forgotten that formula, which I'm sure you guys haven't, but that formula is H2SO4, okay? Or sometimes it helps us a little bit if we actually refer to it as HOSO3H, same sort of deal, but it tells us a little bit more about the structure and what's going on in the reaction. So that's acids. Now, here's the really important part of this whole section is the question is, if we've got a double bond and we're breaking things, where does it go? Now, if it's symmetric, okay, like if we went back to our last one, if it's just ethene, it doesn't really matter where the hydrogen goes and where the chlorine goes. It's essentially the same thing in either case. But what happens if we've got something like propene, where it's obviously not symmetric, and it matters if I add the OH here at the end or if I add the OH here in the middle? Those are two different molecules, okay? We've got isopropyl alcohol and we've got normal propanol, okay? And so those are not the same thing at all, and so it matters very much which of the two carbons things go to. And so the way that we can tell that is by something called Markovnikov's rule. So just to sort of illustrate what we could possibly get out of this, if we are going to hydrate this propene, I could get the hydroxyl added to the middle, okay, to this second carbon, or I could get it added to the end carbon. And again, these are two different things. And in fact, these have names. They're called regioisomers, okay? And so we have to figure out which of these two things are we more likely to get. So for regioisomers, we can add it where we only get one regioisomer, or we can get mostly one regioisomer. Tends to be that a lot of reactions tend to be regioselective. That we're going to get mainly one thing. And that's important to us. Yes, again, we can get some of the other stuff, but it's really important to us to know what the main product is, because that obviously is what we're going to be working with most of the time. So how do we know that? Well, this is Markovnikov's rule, and I'm just going to give you a second, hit pause, copy that down real quick. Basically what it says is that if I've got an unsymmetric reagent and I've got an unsymmetric alkene, that the electropositive part of the reagent bonds to the carbon of the double bond that has the greater number of hydrogens attached to it. And you're like, what in the world does that mean? Well, this is one of these cases where I think it's going to work if you see actually what's happening, and then we'll come back to Markovnikov's rule here in a second. So essentially it comes down to this. We've got two types of things that we use in these types of reactions. Now, addition in alkenes anyway, we're going to call this electrophilic addition. Okay, that means that electrophiles are things that love electrons. They're going to really seek out electrons. And nucleophiles are things that have a lot of electrons. So this works out really well for us in our addition to alkenes. The double bond itself is a nucleophile. It's got a lot of electrons there. That double bond is a very electron-rich region. And then the electrophiles, or the reagent part, usually the proton, are going to come in and basically attack that area. Now, if you remember what Markovnikov's rules just said, it said that the hydrogen, the electrophile, okay, the electropositive thing, is going to attack the area with the most hydrogens. Okay, so that means that what's the attachment part, the important part, like the OH or the Cl or whatever that part is going to get attached to the part with the least number of hydrogens. Okay, so that's essentially the mechanism by which we're going to work here. So let's walk through that real quick. So I've got a hydrogen, and again, this could come from an HCl, it could come from an H2O, any of those types of things. We're going to add that to an alkene, and I'm just going to assume that this is asymmetric. It looks symmetric now. We're going to say, hey, I've got one carbon off on this end and three off on this end, or whatever. What's going to happen is that we are going to, sorry, I'm having a real tough time clicking this, is that our double bond, we're going to bond to that hydrogen, okay? And so in this case, I'm going to assume that I've got extra hydrogens over here, and that's why this is going to bond to this particular hydrogen. We'll talk about which one's more likely here in a second. The important part is what you'll notice is by removing this bond here and bonding it to the hydrogen, what I have now done is I've created what is called a carbocation. Okay? You need to get real familiar with that term and use that term a lot. A carbocation is basically just what it sounds like. It's a cation formed on a carbon atom, and that's really important to us in organic chem because we're all about carbons. So, which one does it form to? How do I know which one it goes to? Well, here's the way it works. It is less stable for the carbocation to form where there's a bunch of hydrogens. As you add more carbon connections to it, okay, then it becomes more and more stable. So this is a carbon with 3 hydrogens, so that's a methyl carbocation, not terribly stable. If there's just one carbon coming off of it, which would be our normal alkene, so like say ethene, okay, then that is a primary carbocation, not as stable as these other two. And so as we get up into secondary carbocations, we get up to the state where this is a lot more stable. So if we, say, had a butene, like say a 1-butene where the double bond was on the end. Let me draw that real quick just so you can have an idea of what we're talking about. Then we could easily sort of tell that we're getting a lot more stability in one area. So, sorry guys. So if I've got, and again, you got to sort of fill in your mind here the hydrogens. So if I'm trying to pick where's my hydrogen going to attack, where's the carbocation going to attack, well, this one on the end has nothing but hydrogens on it, so it would be a primary carbocation. But if I add it to this one right here, then that is a secondary carbocation, and therefore that is going to make a lot more sense. So if I get rid of my double bond there, and apparently get rid of everything else the way I'm drawing here, if I get rid of that and get a single bond, then it's much more likely to get the carbocation here than it would be over here, because I've got more carbon-carbon connections over here. What makes carbocations more stable is having more carbon-carbon connections. Okay? And obviously if we can get a case where it's a tertiary, okay, then that is the most stable arrangement. We'll see a lot of that when we get to aromatics in the next section. Okay, so carbocations more stable the more carbon-to-carbon bonds. So let's run through a quick example of this and we'll walk through the whole procedure here. So I'm going to add hydrochloric acid to this. Okay, what's going to happen is that I could get one of these two things. Okay, so hit pause real quick, figure out which one of these two things you think is more stable. Okay, if you selected, okay, the carbocation that is up top here, whoops, ran out of tablet space, then that is correct, because what we have here is we've got 2 carbon-to-carbon connections there. That's a secondary carbocation. If we put it over here, this is simply a primary carbocation, not going to be as stable. So what that means is that the carbocation is going to form then in the middle, the more stable place, the more carbon-to-carbon connections. Now, what does that matter? Well, the hydrogen added here on the end, so that means that what is left, meaning our Cl, is then going to come in and form onto the carbocation. Okay, because the Cl is now minus, it wants to attach to the plus, and boom, we've added on our chlorine to our atom, or to our molecule rather. So, this is just basically the example of the 3 types that we talked about. Okay, the first step is the attack by the electrophile. That's what creates the carbocation here. And then the second step is the other part adding on to the molecule. So the Cl could attach, what's left of the sulfuric acid could attach, and then we could add the OH part of the water could attach. You might be asking yourself, well, why didn't you talk about like a Cl2 or a Br2? And that's because, remember, that's not an asymmetric reagent, so that's not going to follow Markovnikov's rule. It doesn't really matter. You just add 1 to each of them, and so you're just set. It has to be asymmetrical. Both the reagent that you're adding it to, or both the thing that you're starting with, your alkene, and then the reagent that you're adding to it, those both have to be asymmetric for us to have to worry about Markovnikov's rule. Okay, so let's run through that one, finish up that example then real quick. If we know that we form the secondary carbocation there, the chlorine is then going to come in. It's going to attach in that second part. We're going to get 2-chloropropane in this case. All right, we're going to work a lot more examples in class, obviously, but that is essentially the principle by which Markovnikov's rule works. I'm going to simple up the definition a little bit, so you might want to pause and copy that down. But essentially what it means is that we're going to, you went back and looked at the original thing and it was talking about, electropositive and all this terminology that didn't really make a lot of sense to us. Essentially it's going to work. We want the most stable carbocation. We want the thing that we're adding on, the chlorine, the OH, the sulfate part, we're going to add that to the most stable carbocation. We're going to add it to the section that has more carbon-to-carbon bonds to it. That's going to be a more stable carbocation. All right, hopefully that helps you guys get through Markovnikov's rule, and we'll continue on with reactions of alkenes next time.